Swayam Prabha. Digital India. Educated India.
Hello, welcome to Introduction to Composites course. Today is the 5th day of the last week of this course, and today we will continue our discussion about quasi-isotropic laminates, and specifically what we will cover in today's lecture is that suppose I have a composite laminate which has glass fibers randomly oriented. So, that means that in all directions the fibers are oriented with equal amount of distribution. So, we would expect, because fibers are oriented in all directions, that this type of a plate will have quasi-isotropic material properties, because it will have same number of fibers in all directions. So, the question is that how can we predict the Young's modulus, the shear modulus and the Poisson's ratio for such a randomly oriented laminate using whatever we have learnt till so far. So, that is the question. So, the question is that there is a randomly oriented laminate. So, randomly oriented laminate, equal number of fibers in all directions, hence plate should be quasi-isotropic what will be the value of ER. So, ER means Young's modulus for this randomly oriented plate, GR which is the shear modulus for this random plate which has randomly oriented fibers, and mu R which is the Poisson ratio for this plate which has randomly oriented fibers. So, this is the question, okay. And we know everything about the material. So, we know what kind of fibers it has. So, we say that it has glass fibers, we know the Young's modulus of glass fiber, we know the matrix material Young's modulus, and so on and so forth. But this is the overall approach, the question. So, what is known? What is known? That suppose using the same fiber which I am using to make this plate, I make a unidirectional laminate, then for that unidirectional laminate EL is equal to 16.26 GPa. Suppose I know this, and I also know the transverse modulus of a unidirectional plate made of the same material, and the transverse modulus is 4.43 GPa, 4.53. GLT is 1.49 and Poisson ratio is 0.32 GPa. So, this is what we know. So, the question is that can we now from these data, so there is a unidirectional laminate made from the same fibers and these are the properties. From this information can we find the Young's modulus, shear modulus and Poisson ratio for this plate which has randomly oriented fibers? That is what we are interested in knowing. So, how do we do this? So, our approach A, first thing is construct a quasi-isotropic laminate. We construct a quasi-isotropic laminate, and the more the number of layers we put in this quasi-isotropic laminate, the better it will be, because fibers will be spread more uniformly in all directions. But we can always start, in today's class we will just use 3, because that requires less computation. So, we construct a quasi-isotropic laminate. B, calculate A matrix for this laminate and C, extract ER, mu R and GR from A. And how do we do this? We will explain that. So, first I generate a quasi-isotropic laminate. Let us say it is 0 plus 45, 0 plus 60 minus 60. Suppose it has just 3 layers. So, it is 0 plus 60 minus 60. For this kind of a laminate, I can calculate its A matrix, and from the elements of that A matrix, I calculate ER, mu R and GR, and the procedure for that I will explain that. So, we know that A is equal to A11, A12, A12, A22, 0, 0, 0, 0, A66. For a quasi-isotropic laminate, this is the case, and for quasi-isotropic laminate, A11 and A22 is same, right? Actually, I will not write it in the matrix, I will write it separately. So, for quasi-isotropic laminate, A11 is equal to A22, and if it is an isotropic material, I can also write it as ERT times 1 minus nu R square. Okay. How did I get it? Remember, for an isotropic material system, we had said that the elements of A matrix are given here. So, here if E is ER, that is all I am doing. So, that is where I am getting this ER from. So, if the, so this is there. Okay. Similarly, A66 is equal to GR times T, and that equals ER times T divided by 2 into 1 plus nu R. Okay. I make one simpler one assumption here also, just to make mathematics simple, that we assume that the overall thickness of the randomly oriented composite is 1. So, if that is 1, then this becomes, this T goes away. We can keep T, it will get cancelled out later, but just makes our calculations a little simple, that is all. So, I am just making assumption that T is equal to 1. So, the randomly oriented mat is of uniform thickness and its thickness is 1. No, if there is a randomly oriented laminate, it has only 1 ply, because everything is randomly oriented. So, the overall thickness of that randomly oriented laminate is unity, and what will be its A11? It will be ER times T, T is 1 divided by 1 minus nu R square, and so on and so forth. Okay. So, GR times T, T is 1, so this T goes away, and A12 equals nu R ER divided by 1 minus nu r square. Okay. So these are the relations for randomly oriented ply, right, and I can calculate the values of A11, A22, A66 and A12 using the quasi-isotropic laminate which I am thinking about. Okay. So from these relations then I can back calculate ER, nu R, GR and these things. So let us see how we do that. So from these we see that A11 square minus A12 square divided by A11, what does it come out to? This is equal to ER square minus nu R square ER square divided by 1 minus nu R square, the whole thing square, into 1 minus nu R square divided by ER. Okay. How did I get? I am just substituting A11 as ER by 1 minus nu R square, A12 as ER nu R divided by 1 minus nu R square. I am just substituting this here, that is all. So if I simplify this, this comes out to be ER. So if for a quasi-isotropic laminate I know A11 and A12, I can calculate its ER. I can calculate ER for the randomly oriented mat by this relation. Okay. So if for a quasi-isotropic laminate I know A11, A12, then I can say that A11 square minus A12 square divided by A11 will be the Young's modulus of a randomly oriented mat. Okay. Next we will see how does G work out. So GR is equal to A66, that is direct because thickness we have assumed as unity. Okay. So this is the second relation, and the third relation is for Poisson's ratio, and what do we do? A66 divided by A11 is equal to what? A66 is ER divided by 2 into 1 plus nu R, and what is A11? A11 is ER over 1 minus nu R square. So this is on the denominator. ER cancels out. So what we are ending up with is 1 minus nu R divided by 2. So Poisson's ratio for a randomly oriented mat is equal to 1 minus twice of A66 divided by A11. So this is the overall method. So the question, so once again, what is the method? First we find out the A matrix for a quasi-isotropic laminate, and the laminate should have total thickness of unity. The total thickness of laminate should be unity, and then corresponding to that A matrix, if I use these relations, then I can calculate ER, GR and nu R. So with this background, what we will do is we will actually calculate for a material system whose unidirectional lamina has these properties. Okay. So what we do is we construct a laminate and we will say that it has just 4 layers, 0, 45, minus 45 and 90. Okay. So it may not be symmetric, but if I just reflect it on the other side, I can make a symmetric laminate. So that is not the point. Okay. So this is a quasi-isotropic laminate. because it has more than 3 layers, 3 or more than 3 layers, and the angles are in steps of 45 degrees. Okay. And for this we know that EL is equal to 16.26 GPa, ET is 4.53 GPa, nu LT is 0.32 and GLT is 1.49 GPa. So, this is what we know. So, now what we do is first we find out the A matrix for this lamina, and overall thickness is unity. So, each layer is 1/4 thick. Okay. So, first is we find nu TL is what? Nu LT into ET over EL, and that comes out to be 0.089. So, now I know all the 5 parameters, so I can find out the Q matrix for this material, and Q matrix is equal to, so I will directly write down the relation numbers. So, this is Q matrix, this is 16.74, 1.49, 0, 4.66, 1.49, 0, 0, 0, and this is 1.49. So, this is the Q matrix. Now, this has 4 layers, 0 degree, 45 degrees, minus 45 degrees and 90 degrees. So, we have to find Q bar for each of these layers, okay? Because to find the Q matrix, A matrix, I have to find first Q bar and then multiply by individual thicknesses. So, Q bar for 0 degree is same as Q matrix, okay? For 90 degrees thing, Q bar for 90 degree, it is, we just replace 16.74 by 4.66 and vice versa. So, it is this 4.66, 1.49, 16.74, 1.49, 0, 0, 0, 0 and 1.49. Okay. And for 45 degrees, we actually use the relations which we have explained in the class. So, Q bar for 45 degrees, this works out as, so this is for both plus and minus. So, wherever I have a plus sign, so this is 7.585, 4.605 and this is plus minus 3.02. This is also plus minus 3.02 and this is 4.605, 4.605, 7.585 plus minus 3.02 plus minus 3.02. So, this is the Q bar matrix for 45 degrees. So, Aij is what? Is Qij for the kth layer times thickness of the kth layer Tk, and we sum it, right. And what is Tk? Tk is equal to 1 by 4th because the overall thickness is 1. So, basically I add up all the 4 Q matrices and I get, and divide them by 4, I get A matrix. So, essentially A is this matrix 9.1425, 3.0475, and because there is a plus 45 and minus 45, so A16 is 0, 3.0475, 9.1425, 0, 0, 0 and the last number is 3.0475. So, I have found the A matrix for the quasi-isotropic laminate, and now using these relations, these three relations, I can calculate the Young's modulus, the shear modulus and the Poisson's ratio for the randomly oriented mat. So, I find that AR equals A11 square minus A12 square divided by A11, and I plug in all the numbers, I get 8.13 GPa. GR is what? Is same as A66, and that is equal to 3.0475 GPa, and nu R equals 1 minus 2 A66 by A11, and this comes to be 0.33. So, these are the material properties of this randomly oriented mat, and I can make it a little more accurate if I have more layers in the system. The more the number of layers I have in the system, the more accurate these estimates of ER, GR and nu R become. So, the point here is that this is a very useful method not only to predict behavior of oriented laminates, but even if the laminate has randomly oriented fibers, there also we can use these principles to predict the Young's modulus, shear modulus and Poisson's ratio of randomly oriented materials. And these types of materials are used in a large number of applications, boats, fiberglass, tanks and things like that. So, you can predict their properties using this kind of an approach. So, this concludes our discussion for today. Tomorrow we will have some discussion on failure of laminates, and then we will also do an overview of the overall course, and with that we will close our discussion for this course. So, that is what we plan to do tomorrow, and till then have a great time, and I look forward to seeing all of you tomorrow. Thank you.